Hi, everyone. My name is Danny Chen. I'm here to introduce to you guys and talk about Marmaray, which is Uber's open source generic ingestion and dispersal framework today. Thanks for having me here. I'm really excited. So just to introduce myself, my name is Danny. I'm currently an engineering manager on the Hadoop data platform team at Uber. I was a co-creator before I transitioned over to management of this Marmaray framework. And I lead the data ingestion and monitoring team. Previous to this, the logo's a little off, but I worked actually on Twitter. I was one of the core members of the team that started the Manhattan project, which is a key value store that's semantically similar to Cassandra. So I have a lot of love for just storage and data platforms. And just a couple things, random personal things. I really enjoy playing basketball, biking, and I have two little kids that I spend a lot of time playing with. So really love that. The overview or the agenda for today, I'm going to talk about the mission of the Hadoop platform team. Then I'm going to give an overview of what Marmaray is, and then talk about the need for a ingestion and dispersal framework, and deep dive into some of the architectural components of our framework. Then I'm going to talk about how we actually handle completeness monitoring and data deletion, especially in cases like for GDPR. And we'll talk about how we configure and monitor our jobs. And finally, we'll go through some learnings. And hopefully, we'll have some time at the end for some questions as well. The mission of the Hadoop platform team at Uber, I'm just going to read this verbatim. It's to build products to support reliable, scalable, easy to use, compliant, and efficient data transfer for both ingestion and dispersal, as well as data storage that leverages the Apache Hadoop ecosystem. So in terms of the overview, we're going to talk about Marmaray in terms of it is any source to any sink platform, so it is not tightly coupled to any specific technology, and that was something that we were very deliberate in doing. We're going to talk about the ease of onboarding for this ingestion system. Now, we at Uber, and we wanted to make sure that users of our systems, we did not want them to have a prerequisite of requiring knowledge in Spark, Hadoop, Hive, Python, etc. We wanted them to be able to take advantage of our platform literally by just using a mouse and clicking on a few things. So we made a completely self-serve platform for them. And then next we'll talk about, I also wanted to highlight the business impact and importance of data and data store location. So the assertion that I wanted to make here, it's obvious but subtle at the same time, is that when relevant data is discoverable in the appropriate data store for analytical purposes, there's a really huge gain in terms of efficiency and value for your business. I'm also going to make the assertion that the origin of where the data came from is often not where the business impact can be maximized. And so what we're trying to solve with Marmaray is to be able to ensure that the data can be moved to the right location to maximize the business impact. And finally, I'll touch upon the suite of Apache Hadoop ecosystem tools at Uber, that we really had a vision for how Marmaray would fit into what we already had in our big data team, and how it kind of closes the loop in terms of maximizing the impact of all the tools together. So this is our logo. The name Marmaray is basically a visual nod to the rail tunnel that connects Europe to Asia and Turkey. And the two overlapping tunnel entries, my friend created this logo for me, so I told him I would talk about this. It's basically the Venn diagram that Marmaray is any data source to any data sink. So it's analogous to what we have at Uber, that we want to be able to have a data pipeline from any source raw data store into any online data store. Just wanted to let you guys know that this product was open sourced in September of 2018. There is a GitHub link there for you guys, as well as a blog post link that we wrote, actually announcing the product back in September. Now I'll talk about the need for an ingestion and dispersal framework. So why do we need ingestion? So we have multiple data stores that we create data in at Uber. So every time you open your Uber Eats app or Uber app, a bunch of raw data is produced. And that data is stored in multiple places like Cassandra, Kafka, MySQL. There's a proprietary data store at Uber called Schemaless. And we need to be able to bring all this data into our data lake. And the reason why is obviously for analytics and machine learning purposes. And so we want to take this ingested raw data and be able to produce these derived data sets of immense business value. And in order to do that, we also need to have reliable and correct schematized data. Now, in many data lakes, my understanding or my experience is that when data scientists and analysts actually go over that data and they try to use it to produce, to extract any value, it's often difficult because there's a lot of, the data is of low quality. There's a lot of error in that data. They spend a vast majority of the time actually massaging the data to ensure that it's in a form that is able to be analyzed. Now, what we do is we actually ensure that data is reliable and correct using a schema, what we call a schema service, where any data that is ingested has to conform to the schema. If it does not conform to that schema, we actually do not ingest it. It's actually written into what we call, I'll talk about this later, but it's written into what we call an error table so that they can actually query it, fix the data, and ingest it. There's different approaches to this, but this ensures that the downstream consumers and the data analysts can spend most of their time actually analyzing the data versus massaging the data. And finally, there's at Uber, we had the problem of maintenance of multiple data pipelines before the introduction of Marmaray. So we had, I mentioned that we had MySQL ingestion, Schemaless, Kafka, and all these different pipelines, we had a separate code base for that. So if you think about it, there's a separate code base, a separate set of alerts. There's all the subtleties of each code base, and you have to understand the technical debt that goes into it. And maintaining these 4 or 5 code bases was actually became understandably a nightmare. And we had hundreds of alerts a week, and it was not a good experience in terms of maintaining these systems in production. So the vision of what we had was that we will create this this new vision of Marmaray was that we will create this ingestion framework that is a single ingestion DAG or logic, and that everything will go through that independent of the actual data source. And so this will make, we only have to maintain one code base, one set of alerts, and it hopefully should make our lives much easier. In terms of dispersal, now, if we think about ingestion and dispersal, the use cases are really not that different. It's just really, again, moving data from one location to another. So now we've used ingestion to take data from our raw data stores and ingest them into our Hadoop data lake. And now we want to take the data from our data lake and disperse it over to online data stores, usually with much lower latency semantics. And so these derived data sets in Hive, if you think about it again, we have this machine learning and data analysts creating these derived data sets of immense business value. But if you have it in Hive and you're querying for it in real time, it can take minutes to hours to actually get this data out. So if you're opening your Uber Eats app and you want to get restaurant, and we want to serve you restaurant recommendations to drive our business forward, you're not going to wait like an hour to see what we recommend for you to eat. And so the need arose to serve this live traffic. And so what we were able to do is essentially disperse this data to Cassandra, and now you have sub 10 millisecond latency in terms of getting these recommendations. And again, before we had Marmaray, a lot of teams were solving this at Uber in terms of writing their own duplicate and ad hoc dispersal pipelines. However, these were tightly coupled only for their use case. And so it was not generic and reusable. And so we came up with this vision again for dispersal that this Marmaray framework would be used canonically across all of Uber for dispersal needs. And that is the case as of today. And so the main features of Marmaray, again, we have automated schema management. So we talk to a schema service to ensure that that everything that we ingest is of high quality data. Also, for examples like Cassandra Dispersal will automatically create your tables for you. We'll automatically create the primary keys, etc. And we'll update everything as we encounter new columns, for example. We have integration with monitoring and alerting systems. We use M3 monitoring, which is an open source framework as well. And we can create alerts. We actually automatically set up, and when we talk about the self-serve pipelines that I mentioned earlier, we actually automatically set up alerts for our customers as well. It's fully integrated with our workflow orchestration tool. So we have a tool at Uber called Piper, which we can use to run our jobs. Piper is actually built on top of Airbnb's Airflow. And this will orchestrate your jobs for you. And again, in terms of self-serve, we actually automatically create these pipelines for you so the users don't have to write the Python scripts themselves and can focus on actually analyzing the data. We made this extensible architecture. So we were very deliberate in ensuring that everything we created was as generic as we possibly could make it with an eye towards the future and having the platform evolve so we can handle all sorts of future ingestion and dispersal needs. Finally, again, it was open source as of last September, so feel free to take a look at the GitHub and look at the code. I wanted to give you guys a couple of stats in terms of how it's used today. So currently, we ingest over 120 terabytes of data per day. There's 500 billion pieces of data that we actually ingest per day on our pipelines. There's over 5,000 pipelines running, so it is the canonical ingestion and dispersal platform for all of Uber. And it's used heavily by, for example, Uber Eats and Michelangelo for all their needs. I wanted to go into a couple of use cases. So this is just to make it a little more concrete for you guys. I touched upon this earlier, but whenever you open the Uber Eats app, we will take the orders that you've made and ingest that into our data lake. And this is actually from my phone. I like Japanese food, and so when you order the Japanese food, all that data is ingested into our data lake. And what we'll do is we'll run machine learning on that and analytics, and we'll recommend new restaurants for you. So depending on where you live, your location, or what you've ordered before, we'll create these data sets, again, these derived data sets of immense value in Hive. And then, so that's the ingestion component. And then the dispersal component will now take this data in Hive, and we will disperse it over to Cassandra. And now when you open your Uber Eats app, we'll be able to actually give you these recommendations. Another use case that I wanted to highlight was Uber Freight. So Uber Freight is one of our largest, not largest, but one of our most exciting business verticals. It's growing incredibly rapidly, and we're really hopeful that this is going to be another big business for Uber. And when Uber Freight was first bootstrapping their business, they had a lot of data in MySQL. And what they wanted to do is they had no way to actually run these analytics in MySQL. We were able to use Marmaray ingestion and be able to ingest this data in MySQL and be able to help them run analytics in terms of figuring out their business. Now, one thing I wanted to talk about is our old MySQL ingestion framework before Marmaray was completely snapshot-based. So we had to ingest the entire table about once a day because that's what we could do at the highest frequency of what we could do this in, or the highest cadence. With Marmaray, what we can do is we actually have what we call, there's this technology called Storage Trapper, which I also believe is open source, but it basically is a changelog listener to MySQL. So instead of having to do a snapshot-based ingestion, where even if one row changes in the entire table, we would have to ingest the entire table every day. Now we can listen to the changelogs and we can ingest that into Marmaray, and we can do it in a 30-minute increment. And so your data will be much fresher, and the latency is much smaller as well. So if you can imagine how much that really helps the business in order to get data as soon as possible, that's really important. Like even for things like surge pricing, right? Like you can't, if there's surge pricing right now, you can't wait 24 hours and be able to get that information. Like if you can get that freshness of data down to 5 minutes, which is possible with our framework, then you can actually dynamically make changes to account for that. So now I want to talk about the Hadoop data ecosystem at Uber. I'll just touch upon the slide, but we have our data producers. They use our Avro libraries, many of them to write to Kafka, and our ingestion service takes that information, talks to schema service again to ensure that data is schema conforming, and then writes it into Hadoop. Now, I also wanted to touch upon another open source project at Uber called Hoodie. And so if you think about the Hadoop use case, the canonical use case is that data is immutable and usually append only. And so what we built with Hoodie, which Marmaray uses as the storage format, is a abstraction where we can actually do updates and deletes of data. And so it conforms to the concept of snapshot isolation, where readers will never block writers and writers will never block readers. But you have the abstraction that you can actually update your data and delete your data, and it usually happens within less than 30 minutes. And so you can see that data. So I'll touch upon that for GDPR later, but this is a huge component of our system. Underlying in Hive, our data is actually stored in Parquet format, but their Hoodie is kind of a wrapper around that with metadata to give you the abstraction of updates and deletes. Finally, we can take our dispersal service, read the underlying Parquet data, and then disperse it over to online data stores. So this is the Hadoop data ecosystem. So currently, we can ingest from Cassandra, MySQL, Kafka, and Uber schema lists at the bottom. And we ingest that again through Marmaray. Marmaray, I just wanted to touch upon the fact that we heavily leverage Apache Spark. And so everything is built on top of Spark that runs on top of these Piper pipelines. So that gets our data into the data lake. We run our analytical processing, and again, we can disperse to Cassandra. Right now, we support Cassandra, S3, and HDFS. We're adding support for MySQL and other data stores as well. So what sets it apart is, again, it's really designed to be a generic ingestion framework, and it is not tightly coupled to any source or any sink, and we are very intentional with that design to do that. Now, to go into a deep dive into some of our architecture. So if you take a look at this, this slide, we have our input storage systems. I'm going to go into a little bit of each of these components in a little bit. But one thing I wanted to highlight is that we have a chain of converters. So depending on the type of job that you're running, we dynamically create this chain of converters. So we're not tightly coupled to any specific logic. And so so this chain of converters is generic, and we can write to multiple sinks. We can do whatever you want with the data. And again, it is designed for the incremental use case and not snapshot based. So we don't have to ingest a whole table each time, and that's how we can kind of ensure that the freshness of our data we can ensure that our data is as fresh as possible. So the goal is for the data to show up in less than 30 minutes, and it's basically working in mini batches. If you look on the left side, there's something called a work unit calculator, and that's how we determine how much data to ingest per batch. And it also provides us a way to, depending on the data source, we can actually throttle as well to not overwhelm our systems. I'm going to go into each of these components. I'll touch briefly on them. The first one is the schema service. So again, it can support multiple encoding types. Basically, what this does is, we'll talk about the Avro use case. So it'll give us the Avro schema for each table or each Kafka topic, et cetera, as well as the encoder and the decoder for that binary data. Again, this is generic. We have our own custom schema service in Uber, but we can use any schema service that is open source. Our APIs are designed to be able to integrate with them. And then, again, the schema service is to ensure that any data that we have is schema conforming, so that the quality of data in our data lake is high. All schemas are versioned, and we do allow data field changes as long as it's backwards compatible. So next, we're going to talk about the metadata manager. So we designed this is basically a in-memory key value store. It's just basically a hash map, and what happened is based on our learnings from running previous ingestion systems, we figured that we wanted to allow you to store certain data only if the job succeeds, store certain data only if it fails, or other data independent of the success of the job. And so the reason why we do this is we run what we call these job DAGs on our framework, and we allow you to update the biggest use case for this is checkpoints, right? And so if you think about Kafka ingestion, every time you start a job, we will tell you which offset in Kafka to start reading from and the number of messages to ingest. If that job fails, for whatever reason, we do not update this metadata manager. We do not perform what we do. We actually, if the job succeeds, we perform a check and set where we update the metadata manager and we store that data actually in Hoodie. So you move to the new offset, and the next time you can continue. If the job fails, then this metadata manager is not persisted, and the next time the job runs, we start again at the same checkpoint. So that's how we kind of build resiliency into our framework. And so we have atomicity in our framework because of this. And if the job fails, we can discard the state and start over. Again, this is generic, so we can store any type of metadata that you want. We can store like the amount of records that we were able to process, any sort of stats in the future to allow our system to evolve. Next, I wanted to talk about the fork operator. So what happens is, if you think about Apache Spark, everything in the Spark world is lazily evaluated. So a transformation isn't actually performed until an action is performed. So for example, when you call count, now you actually evaluate every single RDD, or resilient distributed data set. And so what happened is we created this fork operator because when we actually read in the data, again, our use case for this, although again we're not tightly coupled to the system, is that we break everything. We tag all the data, the records, into schema-conforming records and the error records. And so the schema-conforming records will continue to be ingested into our data lake. The error records will be written to an error table where users can look at them and fix the data. Now, the Kafka use case, we actually take raw JSON and we convert that data using our schema service into a binary Avro encoded format, and this is very expensive, right? And so if something goes wrong, we don't want to recompute and reread all that data back in. So what we actually do is we tag these records and we call RDD persist on them, and so we can actually get this data later without having to reread all the data from our input systems. Hopefully that makes sense, but it's a really nice efficiency win in terms of versus having to recompute the RDD from disk. And so the fork operator with the fork function, we save them locally on executors again, so we don't have to re-execute the DAG unless the executor goes down. So again, the fork function is applied. We tag each of the records. They're persisted into conforming records and error records, and we're able to get get those schema conforming records really quickly to process them later on. Next thing I wanted to talk about is we intentionally designed the system so that it's very easy to add a new source and new sink. We have an API, for example, every source and every sink, there's an iSource and iSync, and there's like a read function that returns an RDD. There's a write function that you pass in an RDD. And so as long as you implement these, it's very easy to add support for a new sink. Of course, you also have to, what we call the work unit calculator, you have to implement the interface there to figure out how much data you actually ingest per batch. And so in our data lake, we have everything is using generic record. Now, one thing is we call this an Avro payload internally, and it's basically the generic record with some metadata around it. The part that I really want to highlight with this slide is that in that middle data where we have Avro payload, that is a format that is completely agnostic to what the source format is and what the sink format is. So if you actually write the support for this new source or sink, let's say that you add a new source on the bottom left there, right? But let's say you add like MySQL. That data is converted to Avro payload, but Avro payload, you already have support for it for Hive, S3, and Cassandra. So that means when you add that new source, you automatically already have support to convert that into all these different other types, if that makes sense. So, that's a huge efficiency win. Now, of course, we have to make trade-offs. The trade-off here is that we actually have to do two conversions, if that makes sense. We first have to convert the data from the MySQL format into this generic record Avro payload format, and then we convert it back to the actual sink format. So, that is a trade-off we made. theoretically, you can just convert from like if you're doing Cassandra to RocksDB conversion, you can just convert directly from Cassandra SS tables into the RocksDB format, and you don't have to go through this extra hop. But we intentionally did this because of flexibility. So in practice, this hasn't been a big problem in terms of keeping our data fresh, but of course that could potentially change in the future. Again, we support writing to multiple systems. So if you think about that chain of converters that I talked about earlier, there's nothing, it's completely generic, and if you want to be able to write to multiple Hive tables, we actually do support that, and we have that use case that we do support at Uber. Now, everything that what happens is when we actually create these ingestion or dispersal jobs, we actually create a job DAG, right? And so, just like a DAG in Apache Spark, this DAG will run every single node in that DAG will be a converter or a ingestion job. And at the end, after all that's done, we have something called job DAG actions. Now, these job DAG actions actually are, you can configure them to run depending on the success of the ingestion job or the dispersal job. So for example, what you can do is if the job succeeds, you can report metrics for monitoring. So you can report how much data was ingested, how long it took, et cetera. If it fails, then you can report error data, or you can just report any information in general. Also, what we do is actually after the job succeeds, we register that table in Hive. So in the Hive metastore, we will register that partition. Everything is date partitioned in our data lake. So that partition will, at the first time that you create that partition and you ingest data, it will register a Hive metastore, and then it'll be visible for analytics. The need arose to actually run multiple job DAGs together. And so this is a multi-threaded system, and what happens is there are certain topics at Uber that produce, if we're talking about Kafka ingestion and Kafka topics, there are certain producers that produce data very infrequently, maybe a few times a day or a few times a minute. And then there are other data producers, like, for example, trips and some of our financial transactions. You have the QPS in terms of how much you write into Kafka is thousands of times per second. And so these topics, again, they produce data at different frequencies, and we don't want to run these pipelines individually because we will not maximize the efficiency of our Yarn resources. We run everything under Yarn. And so what happens is we group these topics by frequency in terms of how much data we're actually seeing. And so, for example, if you have some topics with not a lot of data, we can actually make the trade-off that we're not going to run every 30 minutes or 10 minutes, 15 minutes. We'll run maybe like every 6 hours at the and get that data in, assuming that that data is not critical for to have fresh data that fast. Now, for other topics such as trips and things like that, where we have to absolutely have the freshest data, we can run that at a much faster cadence and be able to ingest that data with the thousands of messages per second, and also apply more resources for those jobs. Like every job is configured for a certain amount of executors, and so we can figure that out dynamically as well, and be able to make sure that we maximize the efficiency of our jobs. Now, the job manager, again, this is actually what is the component that runs all the job DAGs. And so it is a single Spark job, and we can run ingestions for up to 300 plus topics at a time. Again, multi-threaded, so we can parallelize this. And then we manage the execution ordering for multiple job DAGs. So for the most important topics, we can actually make sure that they ingest first and they complete first. And so we also are able to ensure job and tier level locking. So we actually built in abstraction around Zookeeper. We take a Zookeeper lock for every single topic, so to ensure that we don't double ingest accidentally. This ensures that our metadata systems are correct and not corrupted, so we can maintain the offsets correctly. So now I wanted to talk about completeness and data deletion. So if you think about completeness, like the main challenge here is we want to ensure that all the data that is ingested, that is written to the Kafka topic, for example, is actually counted and ingested into our system. Now, if you're thinking about how some of the topics that we see at Uber scale, you cannot run a query, a select star query, to see the count of the table and then run it from the source data store and then run it in Hive because it's just too expensive. And so we came up with this abstraction. And also, for compliance reasons, we actually do need to know the completeness of the data if we report metrics. And so, so what happened is we came up with a system of bucketizing records. So what happens is every 10 minutes, we have something at the starting point of our ingestion where we actually count the number of records that we see, and then as it goes through our ingestion systems and there's various entry and exit points, we actually count that together and we aggregate them together at the end, and we are able to compare them and produce metrics to M3 and give you a completeness metric. It does not give a 100% guarantee, but it's very close to it, and we actually can configure our jobs so that for topics that are more important, if you have something like below 99% completeness, we can actually fail the job and run again and ensure that you get completeness of data. In practice, we have been able to get like something above three nines in terms of completeness. So we're pretty happy with that. Now, again, we also can't run queries because in certain cases like Kafka, where there's a TTL of data and we have a retention policy, you can't actually run the queries after a period of time and ensure that you have completeness. So again, the high-level approach is we have these input records from Kafka, again, using Kafka as an example. It goes through all these converters, and every step of the conversion will have the success records and error records. We either write them to the error table or we pass them on to the next converter, and there's various exit points. And we have to, at the end, we have the input records, and we aggregate everything that we saw coming out. So the output records, the output error records, and the input error records, we add them everything together and ensure that it matches. I wanted to talk about how we actually previously stored Kafka data in Hadoop and how Marmaray is a vast improvement. So this is our previous ingestion system. And we actually stored, every single executor would store a small file in Hadoop, and we had a background process that would stitch the Parquet files together to maximize the data, the file size to be basically the HDFS block size. Now, this was a very expensive process, and again, if you think about name node pressure, we're creating lots of little files on Hadoop, and that's not a very efficient way of actually going about it, and we actually caused a lot of name node pressure in the previous system on our infrastructure. Now, also, it was very hard to support data deletion in that old architecture because it was append or read only. There's no indices. We had to scan the entire partition to find out if the record is present or not. And the only way to update is to rewrite the entire partition, not just the file, but the entire directory. Again, everything is date partitioned. And then again, with GDPR, we had to update records, and so that was not going to work for us. So this was a big architectural change, and I'm going to talk about what the new one is. So we have something called Hoodie now. Again, talking about Hoodie, and so what happens here is we can actually update individual Parquet files instead of the entire directory. So if you look here on the right, we write these 4 Parquet files with timestamps. And so this is a batch of data in orange. It's completely new writes, unrelated. These are all inserts. I'm sorry, this one is. So this next batch here in orange is actually all new writes that are all inserts and no updates. Now the next batch, what happens is we actually updated some records in Hoodie, again, using this abstraction of updates in our storage library. And so what we do with Hoodie 1.0 is we actually rewrite an entirely new Parquet file, and now queries will go to this file. And so we have a flag in our ingestion system that we tag every record, whether it's an insert or a update. So insert records are bulk inserts into our system, which is very cheap. Updates are a lot more expensive. And so I actually gave a talk yesterday at NoSQL Day about how we use this feature called global indexing to figure out if a record is an insert or update. And so please refer to that. But that's what we use to figure out the system. And so again, we don't have to rewrite the entire file. The entire directory. Let me correct myself. We just have to rewrite that single Parquet file. Now, as an additional optimization, if you think about it, if the Parquet file has millions of records and you only update one record, you actually have to rewrite all millions of records, which is, of course, again, very inefficient. So we actually have something called Hoodie 2.0, which is a merge on read approach versus this copy on write approach. And so what happens in that one, I don't have slides here, but I'll just describe it really quickly, is we, instead of rewriting the Parquet file, we'll actually write, almost like a write-ahead log, we'll actually write avro files that contain all the changes. And this will, this is done asynchronously. I'm sorry, that part is done synchronously in the ingestion job, but it's very cheap because it's just the changes. And then the job completes. And asynchronously in the background, we have a compaction process, which will take these avro change logs and compact it with the existing Parquet to write a new Parquet. But that means that we can make batch changes, so we don't have to rewrite the Parquet file every time a single record is changed. We can wait like a few hours or something and get a whole bunch of changes and then merge them in. And it still allows you to, if you really want to be able to query for it at the trade-off of latency in your queries. So yeah, in this case, we actually do the updates where the new f1_ts3 overwrites the old Parquet file. And that one is eventually dropped and deleted. So configuration and monitoring of jobs. This is just a really quick graph on our M3 dashboard. So you can see how many rows were processed per topic, how far behind we are. In interest of time, I'm just going to skip over that. In terms of learnings, like we use RDD persist a lot. We saw that it was using writing too much off-heap memory. Sometimes yarn would kill the containers. Shuffle server service is a shared resource across Uber, and sometimes we would overload it. Kafka, we had to be gentle in reading the brokers. Sometimes we caused outages because we were just slamming them too much, so we had to figure out how to throttle. And for Cassandra dispersal, we actually use SS table streaming. The initial version didn't have throttling, which was an issue. We actually have that now, and we weren't able to backfill at the time, but that actually has also been fixed. I just wanted to give some external acknowledgments there is a very similar process framework called Goblin from LinkedIn. It's a data integration framework that's also focused on ingestion. Now, Goblin actually uses, so they were very kind, the LinkedIn team, and actually they came and talked with us and gave us, so we actually reused many of their abstractions, but obviously not their code. We're very grateful to that team. And they actually built everything on top of MapReduce. We intentionally decided to use Spark. And so because Spark is in memory, it runs a lot faster. And it's also easy to express basically the business logic in idiomatic terms because you're using functional programming concepts with Spark. Finally, here's some useful links. We have our GitHub links both for Marmaray and Hoodie, which is our storage system. Hoodie was just accepted into the Apache Foundation, so we're really excited about that. And then we have some engineering blogs. So feel free to take a look at that, especially the last one, which is the data partitioning using the global indexing. That's something that we just recently built into our system to figure out if data is inserts or updates. So this was yesterday, but if you're interested, please see the recording for our H-based global indexing talk for NoSQL Day. And my last slide, which is a shameless plug that we are hiring. I'm located in Palo Alto, but we are also hiring for our Seattle and San Francisco offices. There's an email there. Please feel free if you are interested in joining our team and looking for a job. Feel free to email us. And that's it. I think we have like a couple minutes for questions. So any questions? Yes. Yeah. So if you look at my talk yesterday, I didn't go into it in this talk, but we have something called a cell table and a row table. The cell table is basically a change log of all your changes. So if you have an Uber trip and you have to change the price of the Uber trip multiple times because you changed the destination, you applied a coupon later, or you had a bad experience and you complained to customer service and they gave you a discount, or you added a tip like a day later, the change log, in terms of data lineage, will capture every single change, so you can read that. The row table is actually the concept of what is the latest value across the entire trip at a single point in time. So actually, the latest value at this point in time. So we do capture data lineage from that perspective. Yeah. Yeah. Data manipulation before getting into the final table? Yeah, you definitely can. So again, we use schema service and the fork operator to ensure that the data is schema conforming. So that is I guess some of the data manipulation to ensure the data is clean. But there's nothing preventing you from actually adding different converters in our DAG to transform the data into any format that you want, or add additional fields or things like that. In Cassandra, actually, we have the option to, Cassandra dispersal, actually have the option to add the time of dispersal as a separate column to allow for users to query that information easier. Yeah. Yeah. It really depends on what type of transformation. It's hard to answer that question, but it's just basically a RDD transformation, and it can be cheap or expensive depending on what you do. Yeah. Any other questions? Yeah. It is pretty tightly coupled to Hoodie as well, but there's nothing preventing a separate storage format. Yeah. But right now in the open source project, we actually use the Hoodie libraries to write. Yeah. But underlying, it is just Parquet. Yeah. So. Yeah. Yeah. So we don't use orc right now, but there's nothing preventing that as the storage format to be used. Having said that, like, we did use Parquet for the first version, so if you wanted to make that change, it would be something that would be relatively, it's not impossible, but it would be like a moderate change to the architecture. But I definitely understand like the reason for potentially supporting other types of formats. Yeah. New data sources, yeah, we can support new data sources, but the actual storage format in the data lake is Parquet right now. Yeah. Does that make sense? Or, yeah. So right now we just support Parquet, but again, I mean, there's nothing preventing you from writing to orc. But for this product was released late 2017, so you know you have to make a decision in terms of what you want to support, like for a V1 product. So that's what we did. Yeah. But the actual, in terms of data sources and things, we support anything. I think we're out of time. So thanks. Yeah.